Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today our discussion will center on the exercises or the solutions thereof in self-test 11, Form B, and as you recall, that will deal with non-constant rates. And since there's quite a few problems, well, actually the same 10 as always, let's go over to the board and get started. The first few problems deal with constant rates mixed into the same problem. For example, in problem number 1, you can buy 7 pounds at $2.40 each, 3 pounds at $2.10 each, and the question is, how much was the average cost per pound for these 10 pounds? You see, the tendency for most people is to look at the two numbers, and the usual connotation of average is to find the midpoint number, and that's usually obtained by doing what? Adding the two numbers and dividing by 2. See, $2.40 plus $2.10 would be $4.50. Divide that by 2, that would be $2.25. Notice that 225 is halfway between 210 and 240. It's 15 cents more than 210 and 15 cents less than 240. But you see, what happened over here is we weren't working the same number of pounds at each rate, so we shouldn't expect that answer. Or we should expect it, but we're not going to get it. The idea is this. At $2.40 a pound, 7 pounds are going to cost us $16.80. At $2.10 a pound, 3 pounds are going to cost us $6.30. So altogether, we're paying $16.80 and $6.30. That's a total of $23.10. That was for 10 pounds, so per pound would be what? If it's $23.10 per 10 pounds, per means divided by, we divide by 10, that moves the decimal point one place to the left, and we have $2.31 per pound. That may look like a strange number to you, but I'm going to show you that it's really quite reasonable. Before I go over to the next board, let me just review something with you over here. Notice two things over here. One is that out of every 10 pounds, 7 pounds are at one price and 3 pounds are at the other price. 7 out of each, that means 7 out of each 10, that's 7/10, right? In other words, the higher price is taking up 7/10. And also notice that the difference between the two prices is 30 cents. And the reason I bring that out is, suppose I now take 7/10 of the 30 cents. See, I don't take half because it's not equally weighted. I take 7/10 of 30 cents. 30 divided by 10 is 3. 3 times 7 is 21 cents, okay? Now I take the 21 cents and add that on to the lower price because I'm weighted towards the higher price. In other words, I'm going 21/30, 7/10 of the way between the lower price and the higher price. I add the 21 cents onto the 210, and I get my $2.31. It's not a coincidence. Now, for those of you who still feel the answer should be $2.25, let me point out to you that that's what the answer would have been if you were buying the same number of pounds at each price. To make this simpler, for example, suppose you bought 1 pound at $2.40, then you bought 1 pound at $2.10. Altogether, what have you done now? You've bought 2 pounds and you've paid $4.50. So if you've paid $4.50 for 2 pounds, per pound it's half of the $4.50, there's your $2.25. And the same thing works not just with dollars per pound, but also with miles per hour. And I try to reinforce that in the second problem. See, in the second problem, I tell you there are two towns, A and B, that are 105 miles apart. And the information I give you is that in going from A to B, you take 3 hours. And in going from B to A, you take 7 hours. That may not seem like a very realistic speed for 105 miles. That's one of the problems with averages. For example, is it possible that your car broke down and it took 4 hours to fix? Then you drove very carefully to make sure it was fixed correctly. You see, the problem with average speed is that not everything in life is average. That's why we deal with non-constant rates. See, if everything happened at the same rate, life would be a lot simpler. But it doesn't happen that way. That's not important for this problem. I just like an excuse to spout off every so often. But basically, what the problem asks us to do is 3 things. It first of all asks us to find the average speed in going from town A to town B. Then it asks us to find the average speed in going from town B back to town A. And then it asks us to find the average speed for the round trip, okay? And actually, all three parts of this problem are quite simple. The main reason I put them in is to show you that even though the parts are simple, the answer is surprising. The first two answers aren't surprising. You go 105 miles per 3 hours. Per means divided by. That hasn't changed. So 105 divided by 3 is 35. The label is miles per hour. So your average speed is 35 miles per hour. And all that means is that if you had gone at the same speed for 35 miles per the same speed of 35 miles per hour, in 3 hours you would have gone the 105 miles. In the second problem, you see you're still going the same distance. See the difference between distance and rate? You're still going the same distance, 105 miles, but now it's taking you 7 hours. You're going 105 miles per 7 hours. Per still means divided by. So we divide the 105 by the 7, and that gives us 15 miles per hour. See, so far still no trick. 15 miles per hour, 35 miles per hour. The most common mistake that people make on Part C is they say, look, if you went 35 miles per hour one way, 15 miles per hour the other way, 35 plus 15 is 50. 50 divided by 2 is 25. The average should be 25 miles per hour. The problem with that is that you were assuming that you went the same amount of time at both speeds, which wasn't the case in this problem. Remember, it took you 3 hours one way and 7 hours the other way. In fact, before you even do this problem, if you understand what I'm saying, what should you expect the answer to be? You went 3 hours at 35 miles per hour, 7 hours at the 15 miles per hour. Which should the answer for the average speed for the round trip be closer to? Shouldn't it be closer to the 15 miles per hour? Because you were traveling for 7 hours at that speed and only for 3 hours at the faster speed. Well, what's nice about this is we don't have to debate it. We can just check it out. The first way you went 105 miles in 3 hours. The second way you did the 105 miles in 7 hours. So altogether you did a total of 210 miles. It took you 3 plus 7 hours, that's 10 hours. 210 miles per 10 hours. Just divide both sides by 10 is 21 miles per hour. And as we indicated, that comes closer to the slower speed. And again, to verify what we meant by when the answer would have been 25 miles per hour, suppose for the sake of argument you had traveled for 2 hours at 35 miles per hour and 2 hours at 15 miles per hour. You see, the difference is, in this case, you're equalizing the times, but you're certainly not traveling the same distance at both speeds. You see, the first way I'm going 70 miles, the second way I'm only going 30 miles. But the important point is what? I'm going the same amount of time at each speed. I add the 70 miles and the 30 miles, that gives me 100 miles. The total time is 2 hours and 2 hours, that's 4 hours. If it takes me 4 hours to go 100 miles, that's an average of 25 miles per hour. I want you to really understand this because very, very often the reason that people make mistakes is not because they don't comprehend the problem. In fact, that's an interesting aside. Misinterpretation versus non-comprehension. See, non-comprehension means you don't understand. And if you don't understand and you care, you'll ask somebody to explain it to you. Misinterpretation is you think you understand, but you really don't. And the problem with misinterpretation is that since you think you understand, you don't bother asking anybody for help. And you come away with the wrong answer, thinking it's the right answer. And that's why I like to dwell on some of these fine points, just to make sure that you build up your own intuition correctly, okay? All right, now we come to a problem in which we're going to have to use several different rates at one time. Well, not at one time, in the same problem. This is a multi-concept problem. I tell you that grass seed is 89 cents a pound. I also tell you that 1 pound has been shown to cover 175 square feet. And now what I want to know is, with this information, I have a rectangular lot that's 70 feet by 15 feet, and now I want to know how much it's going to cost me to get enough grass seed to seed this lot. Well, see, there's lots of ways I can handle this. First of all, since a pound covers 175 square feet, okay, and by the way, I didn't do it here, and I should have. One of the things I want to keep doing in this course is whenever I say something like square feet, until you get more familiar with this, I want to write it with the exponent. See, feet squared. And the reason for that is, as long as you see that little 2 on top, there's a good chance you'll remember that it's feet times feet, and it will remind you of area. See, I have, what, a rectangular lot that's 70 feet by 15 feet. How do you find the area of a rectangular lot? You multiply the length by the width. 70 feet times 15 feet. 70 times 15 gives me 1,050, and feet times feet gives me square feet. So basically, let me see how I tackle this problem. To find out how much it's going to cost me, since I know the price per pound, I should find out how many pounds it's going to take. And the way I'm going to find out how many pounds it's going to take is I know that 1 pound takes care of 175 square feet. So I could start counting by multiples. In other words, if 1 pound takes care of 175 square feet, how much will 5 pounds take care of? See, remember, in a rate problem, I can multiply both sides of the rate by the same number. So if 1 pound takes care of 175 square feet, 5 pounds will take care of 5 times 175. That will be what? 875 square feet per 5 pounds. So before I even go any further with this problem, I right away know that I'm going to need more than 5 pounds. You see, because 5 pounds will only cover 875 feet. This is kind of a babyish way of doing it, but the babyish way is the best way if it allows you to see what's happening. That's how you pick up speed. Learn to walk, then learn to run. In fact, first learn to crawl, then to walk, then to run. Okay, now the faster way of doing this is to say, okay, I'm counting by 175s. What multiple of 175 is 1,050? See, 875 was the 5th multiple of 175. What multiple of 175 is 1,050? That sounds like a multiplication problem. Hopefully by this time you recognize it as a division problem. I'm going to take 1,050 and divide that by 175. And I could do that on the calculator, but every so often I like to do something without the calculator so that we don't become calculator dependent, especially for easy problems. I get 6. My goodness, if I had just gone one further over here. Isn't that interesting? I should have known that. If I add 175 onto 875, I get 1,050. Isn't that nice? Do you think I really didn't know that? I'll let you guess, the lady in the tiger story. What I want you to see is how common sense and rigor and formulas go side by side. You don't say which is better. You just utilize the best of all three. At any rate, this tells you what? That it's going to take 6 pounds. Each pound costs 89 cents, so you're going to have to pay 89 cents 6 times, and the answer is $5.34. And if you want to do that by ratios again, see, instead of saying 1 pound takes care of 175 square feet, since a pound in terms of money is equivalent to 89 cents, you can say it's going to cost you 89 cents per 175 square feet. And then what you're going to say is, I think I just copied something wrong over here. Then what you're going to say over here is that since 175 goes into 1,056 times, if I multiply this side by 6, I multiply this side by 6, and that gives me the same $5.34 I would have got the other way. Okay? And now that we've introduced the idea of area, let's go one step further and see if you can incorporate 2 major thoughts at the same time. See, in the textbook, I asked problems like the area of a square is 4,900 square centimeters. And you see why I like to write it this way? That's going to remind you that you're not dealing with perimeter. See, if it was perimeter, it would be measured in centimeters. The fact that I've put the 2 up here, that's reminding you hopefully of what? Centimeters times centimeters, length times length. Okay? Now, in the textbook, I asked questions like if the area of the square is 4,900 square centimeters, how long is each side? See, now we've graduated by 1 level of sophistication. I've bypassed asking you how long each side is, but I'm going to require you to know that, because what the problem says is, based on this information, what is the perimeter? See, now you have to know what the perimeter is. And the perimeter is the total distance around, isn't it? And for a square, all 4 sides have the same length. So to find the perimeter of a square, you take the length of one side, multiply that by 4, and that will be the perimeter. In other words, the perimeter is 4 times the length of a side. The problem is I don't know the length of the side. But I do know what? That the area is 4,900 square centimeters. Square centimeters means centimeters times centimeters, so the length of the side is in centimeters. The only problem that remains is, what number do I have to multiply by itself to get 4,900? Well, you may have recognized that 7 times 7 is 49, and 10 times 10 is 100. So you may have recognized that maybe the number you want over here is 70. The nice part is that if you didn't recognize that, you could do what? You could use trial and error. You could say 100 times, you could say 20 times 20 is 400, that's too small. 50 times 50 is 2,500, that's too small. You could use the calculator, and what do you do in the calculator? Enter the 4,900 and press the square root sign, but either way, you're going to get what? 70. 70 times 70 is 4,900, and because the label was square centimeters, the label here is going to be centimeters. And now you see, now that we know the length of each side is being what, 70 centimeters? Now I multiply that by 4, and so the perimeter is what? 70 centimeters times 4 is 280 centimeters. The most common mistake that people make in this problem is they say a square has 4 sides, the area is 4,900 square centimeters, they divide by 4. The kindest thing I can say about that, other than saying don't do that, is to pat you on the back if you did that and say, gee, I'm sorry, you got the right answer, but it was to the wrong problem. You see, if the perimeter was 4,900 centimeters, in other words, suppose the distance all the way around the square was 4,900 centimeters, then since each side is 1/4 of the perimeter for a square, then I would take the 4,900 and divide that by 4. See, under those circumstances, the length of each side would be 1,225 centimeters. But the key to the problem is you saw the label. See, dimensional analysis is very important. It not only dictates what to do, but sometimes looking at the label reminds you of something that you might otherwise have forgotten. As soon as you see centimeters times centimeters, centimeters squared, it's the amount of space inside a region. And if you were to see centimeters with a 3 on top, centimeters cubed, that means it's what? A 3-dimensional figure. And you're multiplying length by width by height. You see, centimeters times centimeters times centimeters. And by the way, that's called cubing a number, and the inverse of that is called finding a cube root. And those are the kind of things that we do gradually as we go into more and more advanced material. Keep in mind that the advanced material is simply one step at a time going beyond what we're already doing here. Just trust me on that. If you stay with me for more subjects, you're going to find that in a certain manner, things get easier. Now, you may test your aptitude in cases like this. I always like to think of our sequence as being like a marathon. We all start out together, and people drop out at different places. Some drop out voluntarily, some drop out because they just can't go any further, but the only difference between this and a marathon is that if you play the game hard and I play the game hard, wherever you drop out, you're a winner. You're still going to be that far ahead of where you started. And my contention is that most of you can go all the way with the math sequence here if you'll just take it one step at a time and not look at the whole job at once. But enough philosophizing for the time being. Let's go on to the next problem where we again have to think of 2 problems at the same time. Problem number 5 says the circumference of a circle is 200 inches. Now, we've had problems that started like that before, but before the question would say something like, what is its diameter or what is its radius? See, now look what the problem says. See, it says the circumference of a circle is 200 inches. To the nearest whole number of square inches, what is its area? See, basically, we're being asked to find a relationship between the circumference of a circle and its area. Have we yet learned the formula that tells you how to find the area in terms of a circumference? See, we've had the area in terms of the radius, but not the area in terms of a circumference. And by the way, I shouldn't have brought that up, because whenever you bring something up in a self-paced, self-contained course, you sort of owe it to the student to follow the thing through. So I've locked myself into giving you an optional note at the end of this example. By optional, I mean for those of you who have had enough. You basically ignore what I'm saying until you hear me mention the next problem. But for those of you who are interested and feel like following me, I think you'll find something interesting about this. You see, the problem is this, and I want to show you the logic of mathematics. From the circumference, I know how to find the radius. But I don't know how to find the area. But let me just summarize everything I know. That's a terrible statement. Not everything I know. Everything I've told you about circles. I've told you that the area is pi times the square of the radius. We've used that in the module. I've told you the circumference is pi times the diameter. We've used that in the module. And I've told you that the radius is the diameter divided by 2, half the diameter. Now let's look at this as a puzzle. In this particular puzzle, we're starting out, see, S is for start. It's a lousy S. S is for start, that's the circumference, and A is the finish. We're starting at C, we want to finish at A, but the way this game is played, I can only move according to these 3 rules. So from this formula over here, I certainly can get from the circumference to the diameter. Once I'm at the diameter, this formula over here will tell me how to get to the radius, and once I'm to the radius, this formula over here will tell me how to get to the area. Do you see the chain rule, the chain reaction here? I take, as they say in sports, I take whatever the defense gives me. They gave me the circumference. I have to get to area, and my game plan is to get there one step at a time, where at each step I'm using bona fide information. Now, let me verbalize this. See, what I said is I was going to go from the circumference to the diameter, from the diameter to the radius, and from the radius to the area. Now, how do I do that? Let me just incorporate quantitatively the 3 steps I've just mentioned. See, I'm given the formula that C equals pi times the diameter. Remember, in this course, we're always using pi to be 3.1416, unless otherwise specified. So it's C equals pi times D, so the 200 inches equals 3.1416 times the diameter. That looks like a multiplication problem, but to find the diameter, I now take what? The 200 inches and divide that by 3.1416. I keep track of the labels over here so I know where I am at all times. That would give me the diameter. By the way, just for showing you how to do this, I've written the answer out. If I had my calculator here and I was just going for the final answer, I wouldn't write this yet. I would just have this locked in to the display on my calculator. But that's what? That's the diameter. From the diameter, how do I get to the radius? I take the diameter and I divide by 2. So with my calculator, this number is already locked in. I just press the division sign, enter the 2, hit the equal sign. Now this lights up, and the label is still inches. Now what do I want to do next? From the radius, I can find the area of the circle. How do I do that? I square the area, I square the radius and multiply by pi. Well, again, the radius is already locked into my calculator. If I have a button on my calculator that looks like this, it's called the squaring button. I just press that button and this lights up. The problem is if I don't have that button, then I conceivably have to do what? Copy this number down so I don't forget it. And then I do what? I enter this and multiply it by itself. But in any event, that gives me the square of the radius. And by the way, what's the label now? I've multiplied inches by inches. That gives me square inches, and that already tells me I'm on the right track towards finding area because the label is correct. And what's the final step? You take the square of the radius and multiply that by pi. We're using 3.1416, so we multiply the 1,013.207098 by 3.1416. That gives us 3,181.091419 square inches, and the problem says round off the answer to the nearest whole number of square inches, so this would be the answer. And by the way, if I were doing this problem longhand, there's an awful lot of digits to keep track of over here. So people tend to round things off early when they're not using a calculator. The advantage of using the calculator is it's no more difficult to work with this material with all these digits because the calculator is doing it for you. So my philosophy is when you have a calculator, never bother rounding off. Just go through all the operations, go down to the last step because there's been no rounding off yet, then round off after the final step. Because if you start to round off earlier, you start to rounded off numbers and you're compounding errors that way. But at any rate, this should be the answer you get for that problem. And now here's where I come to the optional part of what I told you I was going to do here. For those of you who are interested, I'm going to show you how formulas are generated in mathematics. And the first step towards generating a formula is to remember what you did with numbers and now do the same thing with the letters. See, most people get frightened when they start using letters in place of numbers. That's one of the reasons that algebra gets hard for many people. And we're going to talk about that in Module 12, but for the time being, let me show you how this works. Let's recapitulate what we did, only now I'm not going to put the numbers in. I'm just going to work with the letters. See, the first thing I said was I'm going to use the formula that C equals pi times D, so that given C, I can compute D. And how did we do that? To find the diameter, we took the circumference. That happened to be 200 inches, but I'm just going to call it C here, because it could have been 300 inches, it could have been 500 meters, I don't care what it is. But how do I find the diameter? I take the circumference, and I divide that by pi. And in the language of common fractions, you write that as what? C over pi. What did I do after I had a diameter? After I had a diameter, I divided that by 2. See, the radius is the diameter divided by 2. But the diameter was C divided by pi. So now I divide that by 2. And watch how this happens one step at a time. It may look complicated, but it's still one step at a time. How do you divide by 2? That's a Module 5 problem. To divide by 2, you change the division to a time and invert. So this becomes C over pi times 1/2. How do you multiply two fractions? You multiply the two numerators, that's C times 1. Multiply the two denominators, that's 2 times pi, which we write as 2 pi. See, it's like saying 2 pies. See, 1 pi 2 times is 2 pies. Here we're just saying 2 pi. So it's C over 2 pi, okay? Now I have to square it. Square the radius. How do you square a number? You multiply it by itself. So I take C over 2 pi, and I times that by C over 2 pi. C times C is called C squared. 2 times 2 is 4. Pi times pi is pi squared. That's R squared. Now how do I find the area? See, the area is just taking the square of the radius and multiplying that by pi. Pi is the same as pi over 1, isn't it? And pi squared is the same as pi times pi. Notice that the pi in the numerator cancels with one of the pi's in the denominator. What does that leave you with? You still have a C squared in the numerator. In the denominator, you've rewritten pi squared as pi times pi. You've canceled one of the pi's, so all you have left is 1 pi in the denominator. And how do you read this? C squared over 4 pi. And that's the same as saying what? C squared divided by 4 pi. And this is a very exciting formula. See, what I've done now is I've shown you how old formulas can be combined to form new formulas. Suppose you now had 500 problems to do, where in each of those 500 problems, you were given a circumference and had to find the area. Instead of going through all the steps that we did, what does this say? It says take the given circumference, square it, see, multiply it by itself, and then what do? Divide by 4 times pi. In other words, I'll leave this as a genuine homework problem for you to see if you get the same answer. Take, what did we say, 200 in this problem? The circumference was 200. Take 200, multiply that by itself, then divide that answer by 4, then divide that answer by pi, and you should get the same answer we got before. You see, basically, one of the things that we try to do in mathematics is to find, from all the given information, the simplest relationship between what we know and what we want to find out. In that sense, mathematics is the language by which we paraphrase the universe, the physical universe, okay? But again, enough about that. We have other applications to go through. Problem number 6 says, if there are 2.54 centimeters per inch, how many cubic centimeters are there in 4 cubic inches? This is something that's become a big deal now when we deal with foreign cars, where the foreign cars are measured metrically, the American cars are measured in English units. So in American cars, we talk about engines with cubic inches. In foreign cars, we talk about engines with cubic centimeters. Sometimes you hear the word liter, not L-E-A-D-E-R, but L-I-T-E-R, not to be confused with liter. Liter is 1,000 cubic centimeters. And basically, you see, with automobiles and engines and capacities, we're also concerned with what? How you switch from metric to English. So, for example, if there are 2.54 centimeters per inch, how many cubic centimeters, usually abbreviated cc's, are there in 4 cubic inches? I think you can guess the most common wrong answer that people give here. They say, okay, there's 254 of these in 1 inch, so in 4 inches there'll be 4 times that. Notice the key here, the word cubic. And cubic means to the 3rd power, cube. And that's why we write cubic inches as inch with a 3 on top of it. And that's to remind us that we want inches times inches times inches. Can you visualize that? If you had a 1 inch cube, that's called 1 cubic inch. It's 1 inch by 1 inch by 1 inch. See, what you're really saying over here is, if you have 1 cubic inch, That's 1 inch on each side. But what's another name for 1 inch? Another name for 1 inch is 2.54 centimeters. So you could have, instead of saying 1 inch times 1 inch times 1 inch, you could say what? 2.54 centimeters times 2.54 centimeters times 2.54 centimeters. So in 1 cubic inch, there are what? 2.54 times 2.54 times 2.54. That's 2.54 to the third power cubic centimeters. Again, if your calculator has a y to the x key on it, you enter the 2.54, press the y to the x key, enter the 3, hit the equal sign, and what you'll get is 16.387064. If your calculator doesn't have a y to the x key, what you do is you enter 2.54, hit the time sign, enter 2.54 again, hit the equal sign, then enter what? The time sign, enter 2.54 again, hit the equal sign, and you should get the same answer. Okay? Regardless of how you do it, 2.54 to the third power means 2.54 times 2.54 times 2.54, and the answer is what? This little messy 16.387064. By the way, if I want to round this off, I now have a brand new conversion factor. See, if I'm working relatively loosely with volumes, and I have to switch between cubic centimeters and cubic inches, what do I say? Well, this 0.38, I'll just round that off. It's roughly 16 cubic centimeters. In other words, roughly speaking, every time I see a cubic inch, I'm going to multiply that by what? 16 to convert that to cubic centimeters. And if I need a more accurate measurement, what will I use? Well, to the nearest tenth, it would be 16.4. And to the nearest hundredth, it would be 16.39. And to the nearest thousandth, it would be 16.387. But what have I done here? I've constructed a new conversion factor, a new rate, that tells me how many cubic centimeters there are in a cubic inch. Now that I know this, oh, by the way, I inadvertently wrote something here, and I was going to erase it. I don't think I've used this before. A common abbreviation in mathematics is 3 dots, 1 on top and 2 on the bottom, and it stands for the word therefore. And don't ask me how you get therefore out of that. Everything has to stand for something, so this stands for therefore. So if 1 cubic inch has this many cubic centimeters, 4 cubic inches will have this many cubic centimeters, and that rounds off to 66 cubic centimeters. And you see, the trick is, if you had said, okay, how many cubic centimeters are there in 4 cubic inches? See, if you wanted to use the dimensional analysis of converting cubic inches into cubic centimeters, see, the trick would be what? You still want to go from cubic inches to cubic centimeters, but the trick is you don't want to use 2.54 over here. You want to use what? 16 point, well, whatever we had over there. You see, the conversion factor from centimeters to inches is not the same as the conversion factor from cubic centimeters to cubic inches, in much the same way that even though there are 3 feet to a yard, there are 9 square feet to a square yard. And by the way, problem number 7 just puts the problem into reverse. Problem number 7 starts out giving you a metric volume and asks you to convert it to an English volume. See, problem number 7 says a liter is 1,000 cubic centimeters. How many cubic inches are there in 2.4 liters? So basically, you want to go, in terms of fill in the blank, you want to go from 2.4 liters into cubic inches. And the thought process is what? In the previous problem, we just figured out how to go from cubic centimeters to cubic inches. So now I'm going to go from what? Liters to cubic centimeters to cubic inches. So what I say is, okay, I'm starting with 2.4 liters. I get rid of liters, bring in cubic centimeters, get rid of cubic centimeters, bring in cubic inches. Let me see if my dimensions are right. Yep, I've got cubic inches now. Now, what are the conversion factors? Cubic centimeters and liters, well, they just told me there were 1,000 cubic centimeters to 1 liter. What's the conversion factor between cubic inches and cubic centimeters? In the previous problem, we found out that there were 16.387064 cubic centimeters per 1 inch. Now the problem is all done. From here on in, it's the calculator's baby. We just multiply 2.4 by 1,000, divide by 16.387604, and the answer comes out to be 146.456 0.9858 cubic inches, which rounds off to the nearest cubic inch as 146 cubic inches. In other words, in a 2.4 liter engine, there are 146 cubic inches. And that's basically how this is done. And by the way, is this the right answer, even if you have no feeling as to what a liter is or what a cubic inch is? Sure. It's nice to have a feeling for it, but the beauty of the mathematics and the understanding of the mathematics is you can get the answer without even knowing that. Okay? And now, problems 8, 9, and 10 turn to that part of, remember in this module, we dealt with 3 special areas of non-constant rates. Mixtures of constant rates, which we've just gone through, the study of areas and volumes, which we've just gone through, and then finally exponential growth, which we illustrated in terms of compound interest. So problems 8, 9, and 10 deal with that, but before I get into that, I have to explain one more misprint. It was an obvious one, but it was still a misprint. Since I'm dealing with a 6% interest rate in problem number 8, the problem should have read 1.06 to the 12th power is approximately 2. For some reason that I don't know what happened other than a typo, I put an 8 in there. In other words, this certainly has no bearing on any problem which is dealing with 6%. But with that in mind, here's what problem number 8 says. It says if $6,000 earns interest at a rate of 6% compounded annually, how long will it take for that amount of money to grow to be $48,000? You see, the key point to this problem is every year that the money is in here at 6% compounded annually, you have 1.06 of the previous amount. In other words, after 1 year, you have 106% of your $6,000. After 2 years, you have 106% of the 106%. And the next year, it's 106% of the 106% of 106%. In other words, every year, you're taking 1.06 one more time. So you see, after 12 years, 1.06, the 6,000 will be what? 1.06 to the 12th power times 6,000, okay? And by the way, if you have the y to the x calculator, this is a very easy problem to do. You enter the 1.06, you press the y to the x key, you enter the 12, you hit the equal sign, and what happens is you get the exact amount. You may recall at the top of the problem I put an equal sign with a dot on top of it, and the reason is that on my calculator, if I compute this exactly, I get 2.0219. But because I don't know whether you have that kind of a calculator or not, what I did was I took the liberty of rounding off and telling you what would happen here. In other words, when I say to you, when I tell you that 1.06 to the 12th power is approximately 2, remember, after 12 years, how much money are you going to have? 1.06 to the 12th power times 6,000. But 1.06 to the 12th power is 2. And that says that what's happened? In 12 years, your money has doubled. What's going to happen next? See, if your money doubles in 12 years, every 12 years it's going to double if the rate stays the same. See? That's why the banks sometimes change the rates, because sometimes the economy gets worse, sometimes it gets better. They only guarantee the rates for so long. But suppose this rate was guaranteed. You see, look what happens. You have $6,000 now. After 12 years, you're going to have $12,000. See, not because the 12 here goes with the 12 here. That's just a coincidence. It took 12 years for the money to double. So you see, what's going to happen is 12 years later, you have $12,000. During the next 12 years, the money doubles again, so you have $24,000. See, what's doubling? The $12,000. And then 12 years later, that means 36 years after you've put it in, the $24,000 is what's doubling. That comes out to be $48,000. Do you see what's happened over here? You've earned $42,000 on your original investment, and it's only taken you 36 years to do that. That's well over 15% a year based on that rate. But by the way, this 48,000 is a low estimate because the true value would have been See, actually every 12 years, a dollar becomes worth $2.02, not $2. So actually you'd have a little bit more than the 48,000 here. And again, as I say, if you wanted to get the exact answer to this problem, on your calculator, if you don't have a y to the x key, this problem is a real nuisance because you have to multiply. It's that here kitty, kitty, kitty problem again. It's 1.06 times 1.06 times 1.06 times 1.06 times 1.06, etc. That's tiring even with the calculator. But if you enter 1.06, press the y to the x key, enter the 12, hit the equal sign, okay? That will give you this number over here. While that's still in there, hit the time sign, enter the 6,000, and that will give you the exact money at the end of 1 year, and then you can multiply, at the end of 12 years, and we can work the problem that way. Now, to show you how fast the money is growing, what the advantage of compound interest is, problem number 9 was just a silly little thing to try to show you exactly what's happening. See, in problem number 9, it says if 1.06 to the 11th power is approximately 1.9. And what does that mean in plain English? It means that after 11 years, $1, if it's been invested at 6% interest compounded annually, after 11 years is worth $1.90. That's what that says in plain English. And that's rounded off again, you see, because as I say, I don't know whether you have the y to the x key, and if you don't have the y to the x key, I don't know why I want to keep you busy doing all of these little manipulations. So to make the problem easier for you, I give you this approximation. But now the question is, if 1.06 to the 11th power is approximately 1.9, how much did your investment earn during the 12th year? This may seem kind of confusing, but somehow or other, I suspect that you will guess that you were supposed to use this information someplace. That's the great thing about an American problem. If something is in there, it's got to be used. Nothing upsets students more than to have a piece of information in a problem that they don't need. And yet the irony is that the hardest part of solving a problem in real life is before you even start the problem, the major job is what? To separate out from all of the information what is relevant to the problem and what isn't. But at this stage of the game, I'll tell you the relevant stuff. Okay? But let's just take a look and see what happens over here. You see, in problem number 8, we saw that after 12 years, each dollar is worth $2. This problem 9 tells us that after 11 years, each dollar is worth $1.90. Well, see, now we have to come to some English grammar. What do you mean by during the 12th year? See, during the 12th year means everything from the end of the 11th through the 12th. In other words, during the 12th year means from what? The first day of the 12th year to the end of the 12th year. So how do I handle that? See, at the end of the 12th year, I had $2. At the beginning of the 12th year, I had $1.90. Therefore, during the 10th year, I made 10 cents. I'm sorry, during the 12th year, I made 10 cents. That's interesting. That's 10 cents what? Based on $1. And 10 cents per dollar is 10%. Remember what I invested this money at? This money was invested at what? 6%. But since the money is earning interest on the interest, what this says is that during the 12th year, my money is earning as if I had just put it in there at 10%. In other words, based on the original investment, on the original $6,000, that $6,000 during this year is earning the equivalent of 10%, not 6% anymore. Because I've been getting what? 106% of 106% of 106%. Well, anyway, that's just 10 cents on each dollar. I have $6,000 in there, so I'm going to get 10 cents 6,000 times. You see, look at it this way. I'm making what? 10% of the $6,000. See, 10% means what? 10 cents on each dollar. That's a rate. So now you see I just take 10% of 6,000. That's $600. See, another way of doing this is if you don't like to work on this $1 at a time, simply say what? At the end of the 12th year, this was how much the money was worth. At the end of the 11th year, this is how much the money was worth. So if I subtract the worth from at the end of the 11th year, which is the same as the beginning of the 12th year, you notice that the end of the 11th day is the same as the beginning of the 12th day, things like that. But anyway, if I now subtract what I had at the end of 11 years from what I had at the end of 12 years, that tells me how much I earned that year. And by the way, the distributive property is a very nice way of subtracting here. Do you notice that the 1.06 to the 12th and the 1.06 to the 11th are both modifying 6,000? So I can subtract the regular way. I subtract this from this, and the noun is still what? 6,000. But in problem number 8, I told you this was 2. In problem number 9, I told you this was 1.9. So this minus this is 0.1, which is the same as 10%, times 6,000, and that's going to be 600. And all I did over here was draw a very non-fancy diagram to indicate what's meant during the 12th. See, from the beginning to 12 is what happens during 12. See, this is what happens during 12 years. From here to here is what happens during the 12th year. See, don't confuse 12 years with the 12th year. Okay, now the last problem deals with something that banks do to make things more attractive. See, rather than pay you the 6% once at the end of the year, what they'll do is they'll split the difference. They'll give you 3% after 6 months and then 3% after the year. And at first glance, you say, well, isn't that the same thing? Isn't 3% twice the same as 6%? Remember, numbers are still adjective modifying nouns. See, when they give you the 3% at the end of 6 months, the next 6 months, you're earning 3% on that new amount. Do you understand what I'm saying? In other words, every time a new interest period begins, you're earning that 3% on the new amount. So you're not modifying the original amount. Every time it's interest on the interest. So basically, 6% semi-annually means you're getting 3% every 6 months. See, twice a year, semi-annually. So in other words, now in this problem, I give you a new piece of information, so that tells you you're going to use it someplace. I tell you that 1.03 to the 12th power is approximately 1.43. Using my calculator, it came out to be exactly to the accuracy of my calculator, 1.425760887. But I'm just rounding that off to 1.43. Now the problem says, at 6% interest compounded semi-annually, how much money will you have at the end of 6 years? Well, the trick here is that since it's being compounded semi-annually, 6 years means you're going to have 12 interest periods, aren't you? So you're going to get interest twice a year for 6 years. That's 12 interest periods, but instead of 6%, you're going to get 3%. So the formula becomes this. See, in 6 years, you're getting 3% 12 times. So after 6 years, you have what? 1.03 to the 12th power times 6,000. See, you're taking 103% of 103% of 103% 12 times. In the problem, I tell you that 1.03 to the 12th power should be taken to be 1.43, okay? Actually, remember I told you it came out to be 1.42 something. On my calculator, I may have made a mistake here, but as my recollection goes, on my calculator, I think this $8,580 really should have been $8,554, but that's based on the exact amount. In this problem, we're basing things on what? The fact that 1.03 to the 12th is 1.43. So we multiply the 6,000 by 1.43, and that gives us $8,580. And by the way, this rate applies for every 6-year period. In other words, suppose I leave this money in for 6 more years. See, during the next 6 years, I'm still earning 1.03 to the 12th, which is 1.43. But now I'm earning it on what? The $8,580. So 6 years later, I now have what? $12,232. In other words, I got to multiply this by this. And the reason I bring this up is in problem number 8, we saw that $6,000 became $12,000 in 12 years. What happens over here? In 12 years, instead of having $12,000, you have $12,232. See, you've done better at 6% compounded semi-annually. And you see, banks do this. They can either give you what? The whole 6% once. They can give you 3% twice. They can give you 1% 6 times. They can give you 0.5% 12 times. In fact, if you like the decimal system, keep sticking in a 0 here and tacking on a 0 over here. See, 1.006 to the 10th power is how the formula would look if the interest was being given 10 times a year. This is how it would look if it was given 100 times a year. This is how it would look if it was given 1,000 times a year. In fact, what I'd like you to do for the fun of it, if you have a y to the x calculator, I would like you to actually start to compute these numbers where each time you put in one more 0 here and one more 0 here. You see what's happening is this number is getting closer and closer to 1, but this number is increasing without bound. And a very remarkable thing happens. After a while, this thing levels off and approaches a particular number. That number is called it's a power of e. E is a number which comes up in scientific experiments all over the world at all different levels, but I just thought you might enjoy doing this for fun. I also thought you might enjoy seeing what it means when you hear of a bank that says they compound interest daily. Have you heard that? Compounded daily from the day of deposit. All that says is whatever the interest rate is, they divide that by 365. See, they're doing it daily, so you only get 1/365th of it each day. But then they do it what? 365 days a year. And the amazing thing is that number here comes out to be very similar to the numbers we already have over here. And in fact, when they say compounded continuously, they keep running these numbers through, adding more and more zeros here and more zeros here, and whatever that number seems to get close to. In fact, if you do this on your calculator, after a while, the calculator runs out of digits to note the change in it. They won't make any difference after a while. This is all optional. I don't care whether you do it or not. I just thought that as long as I was introducing compound interest to you, I'd like to show you how it really works. The really important thing here is that these are all asides, which is nice, because in a certain manner of speaking, teaching should be nothing more than a series of interesting connected asides. But remember, the purpose of the exercise sets is not to teach you more theory, it's to make sure that you practice on the stuff that was already in the enrichment lecture, in the textbook, and in the study guide. So with that in mind, I think that brings us to the end for today. Keep working hard, keep having fun, right? And keep staying young.